Good morning, students. So, here is part 2 of solid state, class 12th. In part 1, we have discussed about solids, what are the basic properties of solids, how they are different from other states of matter, classification of solids on the basis of various properties, and on the basis of binding forces between constituent particles. I hope you have already seen that part. So in this video, we will discuss deeply about the arrangement, how solids are arranged, what are the constituent particles of solids. For better understanding, I will show you the 3D animation of what I will discuss in this video. So let's start the video. So now we will discuss about crystal lattice further, in which first is crystal lattice, a regular array of building blocks that may be atoms, ions, molecules inside the crystalline solid is called crystal lattice. As you can see in diagram, there is regular arrangement of atoms, ions or molecules. So this is crystal lattice, the 3D arrangement of lattice atoms. Now the block which is showing here in different color is unit cell. Its regular repetition in 3 dimension makes this whole crystal lattice. Next we have unit cell. So the smallest part of crystal lattice which can be repeated in all directions to generate entire crystal lattice is called unit cell. Let's take an example. Suppose if you are not talking on micro level, suppose any building is made up with regular repetition of bricks. So here brick is the unit cell and its repetition in 3 dimension builds the entire building. You can see in diagram also. Next we have lattice point. In unit cell, all the atoms or ions or molecules are represented by small spheres called lattice point. You can see in diagram also. So next is parameters. Parameters mean their dimension, measurable dimension. So different type of unit cells has its own dimensions, its own parameters by which they differ from each other. Its dimension along the 3 edges A, B and C. These edges may or may not be mutually perpendicular. A, B and C are here length, breadth and height of a crystal. Angles between the edges, alpha, which is between edge B and C, beta, angle between A and C, gamma, angle between A and B. As you can see in diagram, these are angles. So total 6 parameters are there: A, B, C, alpha, beta and gamma. Now, classification of unit cell. It is classified into primitive and non-primitive or centered unit cell as mentioned in NCERT. So primitive unit cells are those unit cells in which atoms, ions or molecules, in short lattice point, will be present only at corners. In non-primitive unit cells, lattice point will be present at corners as well as at other position. It is of 3 types: body-centered, face-centered, end-centered. And there is one more non-primitive unit cell, that is edge-centered. In body-centered unit cell, atoms are present at corners and at body center. Here, body center means center of unit cell. In face-centered, atoms are present in corner as well as all face center. In end center, atoms are present in corner as well as in alternate phase.
Unit cells can be broadly classified into two categories: primitive unit cells and centered unit cells. Unit cells in which all the constituent particles, such as atoms, ions, or molecules, are present only at the corners, are called primitive unit cells. Unit cells in which one or more constituent particles are present at positions other than its corners, in addition to those at the corners, it is called a centered unit cell. Based on the position of the centered constituent particle, centered unit cells are categorized into three types: body-centered unit cell, face-centered unit cell, and end-centered unit cell. A body-centered unit cell has constituent particles at all its corners, as well as one particle at its body center, as shown here. A face-centered unit cell has constituent particles at all its corners, as well as at the center of each face. An end-centered unit cell has one constituent particle at the center of any two opposite faces besides the ones present at its corners.
Next is 7 crystal system. What does it mean? It means that all the crystalline solid unit cells has these type of dimension. Different parameters make them different crystal. You have seen crystal of NaCl and copper sulfate pentahydrate. So you can easily differentiate their texture and crystal shape. Because they are different because they belong to different crystal system. So first is cubic, in which A is equals to B is equals to C, means length, breadth, height is equal, and alpha, beta, gamma, their axial angle is equal to 90 degree. In tetragonal, A is equals to B, which is not equals to C, and alpha is equals to beta is equals to gamma, which is equal to 90 degree. In orthorhombic, A is not equal to B is not equal to C, means length, breadth, height is not equal to each other. Alpha, beta, gamma is equals to 90. In monoclinic, same as orthorhombic, their edge length are different, but alpha is equals to gamma, which is equal to 90 degree, but beta is not equal to 90 degree. Triclinic, it is the most unsymmetrical crystal system in which edge lengths are not equal to each other, where alpha is not equal to beta is not equal to gamma is not equal to 90 degree. In hexagonal, A is equals to B, but B is not equal to C. Alpha is equals to beta, which is equal to 90 degree, but gamma is often 120 degree. Rhombohedral, A is equals to B is equals to C, but alpha is equals to beta is equals to gamma, which is not equal to 90 degree. So this means all the crystals belongs to one of these crystal system.
Based on lattice parameters, we have 7 popular crystal systems, namely cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. Let's discuss each in detail. In a cubic crystal system, all the 3 axes are of equal length and are at right angles to each other. The possible lattices are primitive, body-centered, and face-centered, as shown here. Sodium chloride, zinc blende, and copper are well-known examples of this type. In a tetragonal crystal system, the three axes are at right angles to each other, but only two are equal. The possible lattices are primitive and body-centered. Calcium sulfate and titanium dioxide are examples of this type of crystal structure. In an orthorhombic crystal system, the three axes are unequal, but all axes are at right angles to each other. The possible lattices are primitive, body-centered, face-centered, and end-centered. Rhombic sulfur, potassium nitrate, and barium sulfate are examples of this type. In a hexagonal crystal system, two edges are of equal length. Two angles are of 90 degrees and one angle is of 120 degrees. The only possible lattice is primitive. For example, graphite, zinc oxide. In a rhombohedral or trigonal crystal system, the three axes are of equal length and inclined at the same angle, but the angle is not equal to 90 degrees. The only possible lattice is primitive. Calcium carbonate and mercuric sulfide are examples. In a monoclinic crystal system, the three axes are of unequal length and only two angles are of 90 degrees. The possible lattices are primitive and end-centered. For example, monoclinic sulfur and decahydrated sodium sulfate. In a triclinic crystal system, the three axes are of unequal length and all angles are different, and none is equal to 90 degrees. The only possible lattice is primitive. Potassium dichromate, boric acid, and copper sulfate pentahydrate are some examples.
Now, next is number of atoms in per unit cell. First is simple cubic unit cell. We will be calculating this only for cubic crystals and its type, not for others. So first simple cubic unit cell, we call it SCC. See, in SCC, atoms are present only at corners. Each atom at a corner is shared between 8 adjacent unit cells as shown in figure, 4 unit cells in the same layer and 4 unit cells of the upper or lower layer. As we are calculating number of atoms in each unit cell, so we will not include that part of atom that is shared with other unit cells. And after excluding all the shared part of that atom, we will calculate the number of atom in per unit cell. So contribution of an atom, corner atom will be 1 by 8. And since 8 corners are present in a cube, so total number of atoms in one unit cell will be 1 atom. Next is body-centered cubic unit cell, or in short BCC. Atoms are present at each of its corner plus one atom at its body center, as you can see in diagram. The atom which is present at its body center belongs to the unit cell only, so it gives complete contribution to its unit cell. As it is not sharing with any other unit cell, so its complete contribution is towards its own unit cell. So on calculation, from corners 8 into 1 by 8, which is 1 atom, and from body centered, since it is not shared with any other unit cell, so again complete contribution 1 atom. So total atoms in BCC will be 2 atom. Next is face centered cubic unit cell, or in short FCC. In FCC, atoms are present at all corners plus center of all 6 faces, as you can see in diagram. Atom present at face center is shared between two adjacent unit cells. So the contribution of that atom for a unit cell will be 1 by 2 only. If we calculate the number of atoms, so from corners it is again 1, and from face centered, since there are 6 faces and each atom contributes its half, then 3 atom from face centered. So total in FCC will be 4 atoms.
Consider 3 types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distances between the atoms are greatly exaggerated. In reality, the atoms are packed much more closely together, as shown in the space-filling model here. The space-filling model shows that the atoms touch along the edges of the cell. By considering the portion of atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, it is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corner atoms into 1 by 8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. However, there is one more atom at its body center. As a result, the atoms at the corners no longer touch along the edges of the cell in the space-filling model. The unit cell of a body-centered cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1 by 8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corner atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals, and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. It is clear that the atoms at the corners contribute 1/8 of their original volume each. In addition, there are 6 atoms at the 6 faces, which contribute half of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1 by 8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4.
Now next is density of unit cells. See, density can be calculated with the help of mass and volume. So let's assume A with the edge length of any unit cell, m the molar mass of that atom, d is density of the atom. So volume of a unit cell can be calculated will be A cube. Mass of the unit cell will be equal to number of atoms in unit cell multiplied by mass of each atom, which is Z multiplied by m. M can also be written as capital M, which is molar mass upon Avogadro number. So therefore density of a unit cell can be calculated with the formula Z small m upon A cube, small m after substitution, Z capital M, which is molar mass upon A cube into Na, that is Avogadro number. So the main formula of density will be Zm upon A cube of Na, where Na is Avogadro number, A is edge length, Z is contribution of or atoms per unit cell,